There's many days I feel very boring, but there's
Not
it's
boring, bored.
bored. No, not bored. Boring.
On those days, I suggest that you buy a bottle of wine from South Africa, which I think is called Bored Doe, DOE.
Oh, that's cute. I
And it's
miss your puns, man.
yeah,
I miss you
it's a
hanging
red
out.
wine, Bored
Yeah,
Doe.
Bordeaux. Okay.
People start getting in. It's good. Um,
So,
share.
so this is definitely a special case, Alex. So I usually talk a lot about how IC works because there's all IC users here, I'm going to skip that section. Um, I'll leave it available if they want to go over that, but
In the slides, yes.
yeah, but yeah.
Hmm. Here it is, by Windows. The point is not to showcase my face, which don't look anymore like that. That's just for the people knowing where to go.
Uh-huh.
Silencing the phones. They're going to take about an hour with all the slides, right, Terry?
Yeah, yeah. There's a lot to talk about with EPA 1621.
Okay. So it's going to be an hour presentation and then 30 minutes, if at all, for Q&A, which should be plenty. Okay, it's noon time in Pacific time zone, where Terry's going to be presenting from. Welcome everyone to the next IC users meeting session. And in this session, Terry, who is the senior scientist, application scientist in the IC business unit, application lab, is going to present her personal experience with the combustion IC as it is applied to the proposed drafted EPA method for analyzing fully fluorinated organic compounds in the wastewater and similar matrices. The recording will be available on the YouTube channel just at the end of today. And I am displaying right now how to find that particular YouTube channel for those who would like to listen again to the recording of the presentation or pass it on to people who were not able to join live. If you're registered and not able to participate, don't worry. We'll send you the email with a link, exact link to the recording on this YouTube channel. We're going to take about an hour for Terri to present all the results, hints, and all the gotcha to avoid. And then after the hour of presentation of all the slides, we'll have plenty of time, up to half an hour, for all your questions. Brian Lucanville and myself, Alex Semyonov, will be monitoring the chat. So you're welcome to place questions, preferably related to the topic of this presentation today. And we'll try to monitor and answer those questions. At the end of the hour, after presentation is finished, I will enable for everyone the voice, and you can also ask your question with your voice. If you want to, you can switch on the camera at that time, which would be kind of nice to see the face of the person who is asking the question. I turn this over to Terri. Welcome, and thank you.
Okay, I get this going here. All right, so everyone can see my presentation mode. So I'm Terri Christison. I've been with Thermo Fisher Scientific a long time. But before I was an employee, I was a customer. So I'm just like you, love my analytical chemistry. So today I'll be talking to you mostly about the multi-lab study for EPA 1621. And I'm throwing a few tips on how to make a successful implementation. And as well as, of course, introducing the theory of the PFAS and combustion IC. I will do this presentation a little differently than I normally do. I will not be presenting any IC theory because you guys are special. You all know about IC. So I'm just going to talk about combustion IC and EPA 1621. All right, so let's get started. Well, maybe let's get started. Mm. There we go. Okay, so I'm sure everyone knows what this is. This is what started all of our problems here with PFOS. This is a perfluorinated coated cooking pan. And it's been around since the 1940s. It was a very amazing polymer that they invented, but right now it's giving us all kinds of problems. So this is what this whole presentation is all about, PFOS, perfluorinated compounds. So what are they? What are PFOS? They have been nicknamed the forever chemicals. They're perfluorinated perfluoroalkyl substances. 9,000 to 15,000 compounds of concern. The reason why there's a range here is one, they keep adding some every day. Two is different agencies define them differently. So I'm going to give you the EPA definition, which is a fluorinated compound that has two or more adjacent saturated carbons that are partially or fully fluorinated. For example, PFA, perfluorinated acid, is not a PFOS. So the difference in the compounds, of course, are the carbon backbone to different sizes. This one is a C6, and the tail, which is this one is a sulfate. It can be an acid or just an alkyl. And of course, how much fluorination. This particular compound is hexane sulfonic acid, and it's of the PFHX PFOS family. So keep that in mind when we use all these fun acronyms. So why do we care? Other than it's been around a really long time, so there's a lot out there in the environment. It also can impact us, our health, negatively. And the most, tipping it over the edge on top of that is that it's persistent and accumulative. It pretty much impacts hormones in general, seems to be all the issues that they discuss about that. But to me, the most unsettling one is the potential for epigenetic effects, meaning we could pass this on to the next generation. So where's it coming from? Well, pretty much everywhere. I have this really fun diagram over here on the right from the public water systems, from computer chips down on their left, and of course fire extinguishers are quite much in the news, but our stretchy clothes, our food packaging, um, but also, ladies, it's our makeup. I'm sorry. Um, so it's definitely there everywhere. And it's in the air, on the land, in the water systems, and therefore, whether we are eat animals, fish, or vegetables, we're getting it also through our intake, our food intake. It crosses pretty much everywhere. They've found this amazing polymer. At that time, initially, they didn't have any environmental concerns or health concerns, but so it's been used in lots of different industries clear across all what we would consider like markets, from mining to power generation, pretty much everywhere. Like I said, food packaging. Um, We also have another driving force for this analysis is that the EPA has a reporting requirement for PFAS. So all of us manufacturers have to start reporting accumulated data from 2011 to 2022, a 10-year span or 11-year span of PFAS that we've imported or used in our instruments, materials, fabrics, etc. That it just opened up around April 2024, and the deadlines will be coming up in next year. They'll officially start loading data, I think, towards the fall of this year, which is just around the corner. And of course, not only does this impact the things that need to be analyzed, because everyone wants to know if that particular polymer connector fabric does have PFOS, or if it just might have PFOS. They all need to know because they don't want to report anything that they don't have to. But also, what it means is that likely there'll be some sort of limitation set, some sort of regulatory value set after they get all this data. They're not just collecting it just to find out what we're doing, but they have plans for this data. So there are many state regulations on PFAS, from food packaging to fabrics and makeup and etc., and water, of course. But the only federal one we have so far was implemented in April of 2024, and it's for PFAS in drinking water. They have some select PFAS compounds that they're interested in, and they have some rules. So for this year through 2027, we need to monitor the amount of PFAS in our drinking water. And 2027, we need to start telling the public. And 2029, and we need to start implementing fixes, and we're subject to fines if we're out of compliance. So what are those specs? Oh, they're pretty tight here. I'm going to move my cursor here to get to the Alex in the corner. They're PFOA, PFOS, PFHX, PFNA, HFPO, PFBS, and a mixture. Okay, so what are all these compounds? So PFOA, that's perfluorinated octanoic acid. And for drinking water, because it's a daily lifetime exposure, they want it down at 4 ppt, nanograms per liter. And the goal is really to get rid of it completely. PFOS, which is the perfluorinated octane sulfonic acid, is the same situation. The PFHSX, that's the hexane sulfonic acid I introduced earlier, and the PFNA, that's the perfluorinated nonanoic acid, sorry, so C9. And those are 10 ppt. And there's another compound here, which is a trademark compound. It's perfluorinated propylene oxide dimer, is at 10 ppt. Butane sulfonic acid, perfluorinated butane sulfonic acid is believed to be a lot less of a concern. So it's at 2000 ppt, which is 2 ppb. Okay, and then this mixture. So how do you calculate this hazard index? Is that you look at the portion, the fraction you have of these based on the MCL, and if it adds up to 1, then you're at the limit. So for example, look at PFNA and PFHXS. Those are 10 ppt. Let's say if we measure 5 ppt of both of those compounds, and the MCL is 10, that means we're now at the limit for the mix of those two. See if I can get my back the right spot. I lost my arrow. There we go. No. Okay, so we do have some targeted methods on the books. EPA 1633 is an extractable, solvent extractable method. It's in the same stage as EPA 1621, where it's passed the single laboratory and the multi-laboratory studies, and it's in the comment in preparation to be made into a law, official method. But notice it's only good for 40 compounds. So this is really like a fraction of the compounds of concern. Not only that, but we have to buy all those 40 compounds, and we have to total up all the results, identify each compound. So not ideal, but so to me, this is even more important than having to do speciation. So I am an IC chemist, so I have my set of standards and I run and I get results and I'm happy and everything's cool. All right. But this is comparing AOF, which is a non-targeted method, that's adsorbable organic fluorine, much like what is done in EPA 1621, versus a targeted value, which is extractable fluorine. You can see there on the left-hand scale, which is for the blue, which is the AOF, is about 100 times larger than the scale on the right, which is for the targeted PFOS. So it's about 100 times more of doing it through analyzing for PFOS using AOF and CIC rather than extract for PFOS and analyzing by targeted methods. And the current hypothesis is that this is because likely AOF can also pick up many of those larger compounds that aren't as easily extractable, but they are certainly contributing to the total PFOS contamination. So it's just very important. And I do want to tell you before I completely forget, is this graph is from one of our customers, and we've adapted or changed it slightly different. With her permission, we are presenting this data. This is her data, and she has presented it at the NEMC 2020, and she has it published in the ScienceDirect.com Science. So down there in the citation. But anyway, this is really rather fascinating information. We have also seen similar results when we're looking at food packaging material and textile material, that we're actually seeing a lot less unextractable. And, you know, this is really actually a concern. It's contributing a lot more to the contamination, but we may not see it. So, okay, so let's get into the meats of it. So we're going to talk the rest of it about combustion IC. It's probably going to be a little more information heavy, data heavy, but essentially combustion IC uses, it's a way to get around all those sample issues. As chromatographers, you're well familiar with, how do I get my sample into the instrument, right? So I call it IC envy. Our, you know, we provide an amazing analysis. We can determine those corrosive ions. And that really impacts lots of different samples and lots of different transport and through many different industries. But they may not be able to directly test for them because their sample just won't fit in an IC, you know, like a printed circuit board, a bunch of rubber samples, you know, the petroleum industry. Oh boy, you know, they have all these naturalized gas, compressed gas, sludge, and algae oil, and, you know, just darn goo. You know, or, you know, even liquids can be, you know, rather challenging to put directly into an IC. So, or for this analysis, how do you get a gallon of drinking water in the IC? Or how, even for 100 mils, how do you get it into the IC? So again, combustion IC provides, Alex, you're going to have to take over this slide process here because it's not behaving well for me. Can you do that?
I will try from slide 16, right?
Yeah.
Okay, give me a second.
Oh, 15. Go to 15. Well, maybe I can do it. It's just,
Try again because I have hard time.
okay. I just have a problem with advancing the slides. Because they put my footer right there where the little arrow is. Okay, so anyway, the first step for the EPA 1621 is a stage called adsorption with a D. So what we're going to do is we're going to use some SPE type material, only it's for ionic or organic compounds. So we're going to use granular activated carbon columns, two small ones you see over here in the picture there on the bottom, and that's my wrench for size. And there's a carrier, we're going to hold them in place so we can do them in serial. And that's 100 mils of water right there. So combustion IC has, or EPA 1621 has 3 stages of analysis. It's the sample prep before the sample prep, which is the adsorption of the sample under the carbon, and then combustion, pyrolytic combustion, and then analysis by IC. So here's the steps for this first sample step, sample prep station. I have to say that probably the most important thing in this whole process is continuously keeping your eye on baseline contamination. So you want to wash those containers and the tools frequently. And I put it as both the front of the process and the back of the process. So we were given 100 mils samples, but you need to allocate your sample to about 100 mils. You can maybe by weighing it so it only touches the bottle. And add 2 molar sodium nitrate, and then you pump this sample at about 3 mils per minute onto those carbon columns. Now we're going to rinse off all the inorganics using sodium nitrate, 10 millimolar, and then DI water to wash off the sodium nitrate, and then maybe a little bit of air to kind of get it a little dry to, minimize the, exposure to the combustion tube. Now, so what we really want is that carbon, right? So we're going to push out the carbon into the ceramic cups or boats and then start washing again. All right, so then the conditions for the pyrolysis and ion chromatography, this is pretty straightforward. It's essentially combustion without oxygen at a very high temperature, so pyrolysis, then combustion at a very high temperature with oxygen and water vapor, that's the truly combustion. And we're going to have a carrier to kind of collect that sample as a gas into our water, which is the absorption solution. And essentially, that's the whole process for the pyrolysis part. The sample boat or cup is essentially just needs to be in the hot part of the furnace for 5 to 10 minutes. The EPA method says 10 minutes. So that second line there for the boat sample mode, that's the hot part of the furnace. The ion chromatography method, again, is pretty straightforward. The EPA developed this method along with some of our colleagues. They selected the Thermo Scientific Dionix IonPack AS24 column. This is a rather unique column. It's optimized for low molecular weight organic acids, specifically the HAA method, haloacetic acid method. So because of that, fluoride is actually well retained onto this column. So that combined with having hydroxide gradient and a very small water dip, we have absolutely no issues of staying away from the water dip. So that's quite different from a carbonate column and a carbonate eluent, where you struggle to get the fluoride out of the water dip. And the reason we care, of course, well, one, that's our primary analyte, but two, you don't get as good as accurate quantitation if you have to integrate over a curve. So you always want it to be a flat. Anyway, so that's the primary thing. We're using reagent-free ion chromatography. It takes away all the issues with manual element preparation and all the variations and that such. So essentially we, just add water and it generates the element for us. And of course, this is a suppressed conductivity detection. I'm only analyzing 100 microliters out of that 10 mil absorption volume. And I'm sufficiently happy with that. For the EPA 1621, our goal was to achieve ppb sensitivity. So that achieves that. And we can easily inject more sample volume to increase our sensitivity. Okay, this is the flow, kind of a generic flow diagram of this process. And so because it's a sample prep, it's on the right-hand side. So we have to change our point of view from moving from the right to the left in this process. So it's our samples. So in this case, it'd be carbon columns or could be our liquid standards is introduced through an autosampler. And where it goes into the furnace and it's still in the gas phase, goes through the pyrolysis stage first and then the combustion still as gas. And then it's aerated or bubbled or aerated into DI water, the gas absorption stage, and then mixed and injected in the IC. And so here's a chromatogram of two of my samples. Chromatogram A in red, there on the bottom, is my method blank, and the fluoride peak is, of course, peak 1. And sample B, chromatogram B, is one of my MDL standards, and again, in blue, and just to demonstrate some of our data. And shown here with our latest IC, Thermo Scientific Dionix Inuvion. It is RFIC system and really cute and compact, just amazing sort of system. We just love it over here, and we're pretty sure you're going to love it too. Here's a nice flow diagram. Essentially, we have on the left where we have the pump generating our eluent with the eluent generator cartridge, and all that flows into the valve where it picks up the sample and then takes it to the guard and separator columns where it passes through the suppressor and then through conductivity detection. Okay, so take a quick look over there on the right. Don't get too nervous, but that's kind of one of the sequences that the managing lab, General Dynamics Technology Lab, who's the organizer of this study. That's the direction that they gave for us. But I'd say, I'm actually very impressed. I mean, we all know the EPA chemists are very smart and very experienced. This method is a very rigorous method. I'd say the challenges here are what you would expect: baseline contamination. And because of the sensitivity needs, it's cross-contamination issues at all stages, purely expected. And the sample particulates must be analyzed. So I found that a little challenging, but it's because PFOS sticks to everything. We're not allowed to use any glass containers or any glass features in our analysis, but it adheres to plastic and particles and solids as just as well. So we do want to analyze those particles to make sure that we're getting the whole PFOS picture, but it does introduce an extra variable. So the method tactics to overcome these obstacles during the collaboration study only, as they tried to minimize all the variables, just tried to keep just the evaluation of the capability of us chemists and the two instruments that were involved in this collaboration. But it's also another way to think about it too when you implement your method. Fluoride calibration is through the combustion system. So instead of calibrating from an external source in through to the IC, now it passes through the combustion system. So it eliminates some of the potential variations that you might have from it being combusted versus introduced into the IC directly. And all of us who've worked with the EPA before know that bracketing is one of their modes of ensuring that the process is stable and in good check. So that's to ensure that everything's working fine and we're working fine to do the samples themselves. So they introduce dry blanks, and the dry blanks are when you get a new lot of granulated activated carbon, you do check to see if it's similar levels as your previous lots, because these carbon columns were designed for AOX at ppm levels. So there's possibility of an extra contamination problem introduced. And empty boats looks at the system. Calibration verification standards, so CVs, those are to ensure that calibration, as it runs through the combustion system, that it still agrees with the calibration that you've selected for your process. Method blanks and initial precision recovery samples and ongoing precision recovery samples to verify the adsorption. And of course, always they're using is replicate and replicate spike samples. In our evaluation, we spiked at 2 different levels plus replicates, and we evaluated 4 different types of PFOS compounds. Okay, so I split this up under animation just because I thought it was just a little overwhelming, but there are 7 tasks for this for EPA 1621. The first task is the easy one, right? So it's just determining the retention time window. The goal is to have it the retention time more than 1 minute from the minima of the void volume and also less than 1 minute from chloride. So essentially isolated more than a minute from those two features. At that point, there's no process checks because we're just starting, right? All right, so calibration, relative standard error should be less than 20%. And we're still using inorganic standards at this point. We are starting to use our calibration verification standards as process checks. Then step 3 is the method blanks and the MDL standards. Typical EPA, you generate 7 of these over 3 days. That's from the PFHXS. So we're looking at equivalent fluoride from the PFOS standard. This is, again, the start of the adsorption plus combustion IC. In the published method, EPA 1621, they combine this into, excuse me, initial definition of capability. It's a parameter often and found in EPA methods. It's essentially saying, can your lab do this method? Can we then, trust the results out of your lab for this analysis method? And they're looking at 2 parameters plus sort of another one, where it's accuracy and precision. So we do 4 replicates of 15 nanograms per mil. This is ppb from fluoride from PFOS. And we look at the precision and the recovery. Now we're going to use this mean for our ongoing precision and recovery standard that we're going to use. And then finally, we get to do samples. Okay, so we have for our study, we did 9 samples in replicate. Some are high total suspended solids. So these samples, so there are criteria before you can start analysis. The fluoride must be less than 8 ppm, milligram per liter, and the chloride must be less than 100 milligram per liter, and the TSS must be also less than 100 milligram per liter. So if the ionic presence is higher than that limit, then you must dilute down to the limit before you do the adsorption stage. If it's high TSS, then you must use some ceramic wool as a filtrant, because again, we want to collect those solids as well for analysis. And then so that's the samples. Then we looked at recovery of 2 levels of concentration from the PFHXS. And now notice we've added in our ongoing precision and recovery standard. And then finally, we look at the different types of PFAS. The perfluorinated butanoic acid and the perfluorinated octane sulfonic acid. And then there was a blend of 30 PFAS compounds that we also used. So issues, whew, yes, contamination and contamination. I also ran into evaporation of the solvent-based spiking standards. Now, normally we would use glass vials, and often they would have Teflon septa, right? But we can't do that with a method that we're looking for PFAS because we're, shooting ourselves in the foot here. So you must use PFAS-free vials for your solvents and the caps also. So they're HDPE, but I didn't find them as sealable as if it were glass vials with caps. So for me, that was an issue. I recommend that you kind of stage how you're using your spiking solvents just to make sure that the methanol hasn't evaporated. Or you could store it maybe in a minus 80 degrees freezer. It won't freeze. Methanol can't freeze, but it'll keep the evaporation down significantly. But, not to worry, knowledge and practice fixes everything. It's just changing a mindset to deal with the contamination issues. So I've kind of mentioned this before, but I consider this like a trace analysis method. Before I joined Thermo Fisher Scientific, I worked in the electronics industry. And so the first week was pretty rough learning how to do that. But after that, when you adapt your mindset to dealing with trace contaminants and you understand the sources of contamination, it readily becomes the way of life, right? So the easiest one is the cross-contamination from instruments. So we all know we have to keep our instruments clean. You just need to keep an eye on what the baseline levels are and such. The adsorption instrument probably is the one you need to keep the closest eye on. So that's why I said I recommend washing before you start and washing after you finish a lot of samples, a set of samples. So for ours, it was a 6-sample instrument. So after 6 samples, I cleaned the whole system before I started the next one. Tools may be less clear, but yes, of course, they're touching your samples. So, make sure to wash or rinse them with methanol, the tips the tools that you're using, and DI water on top of that. Methanol, some levels of methanol can also contribute PFOS. So just be aware that you should also rinse with DI water to help make sure you get any methanol off of there as well. Less clear also, storage containers and vials. We typically don't have to consider those in most analysis, except for trace analysis. But again, you want to make sure you rinse these and such. The environment, also less clear for most of us, unless you worked in the industry. It it can be situated under an air conditioning vent or a heater vent or someone doing something or sweeping in the other side of the lab or opening a chemical on the other side of the lab. So that really has proven to introduce contamination. And I have heard a recent story that a customer had with PFOS contamination, a sudden change in their environment, and it was tracked down to the HVAC, the air conditioning filters have been changed. Now, I don't know how they solved that problem, but certainly it's something to keep an eye on. The usual are the consumables. We always have to keep an eye on our consumables, um, and and you know, and it is you and I, right? So our personal care products could potentially contaminate our samples. Do we touch our face? Do we, is our perfume? I don't know. It's one of those things you have to watch out for trace. So just throw it in your list. Keep an eye on it. I usually, when I'm looking for a contamination issue, that's usually the last one I work on. But I'm aware that that may be where I'm going to next. Okay, here's the task 1 is a retention time, and I blew up the little water dip there. You can see the minima there, and it's about, I showed my retention time over here on the right. It's about 3.5 minutes. So it's a great window. Yeah, no problems with RFIC. I mentioned a relative standard error. With the new EPA methods, they're pretty much requiring RSE instead of coefficient of determination, R squared or RSD, for determining the best fit of your calibration curve. And essentially, it's looking at the difference between theoretical versus your measured values, and the sum of all of those. So you can take your look at this formula here later, but that's essentially what they're getting to. And after working through this study, I agree with them. It is a better way to do it. However, it's a lot of calculations. I did not find that Chameleon had it at first in their list of calculations, so I did them all manually in Excel. It taught me a little, but I found it after I completed this study. Oh yes, so to save you some of the pain, I found the best way is to insert it into the calibration tab in the interactive results tables, where it shows you what your R squared is, coefficient determination, that slope and all that for your calibration curve. So you just insert a column and select peak calibration type, and then look for relative standard error. But even so, I've also taken another step. I found that you could save it as a setting. So you know how your settings are like a default setting. So every time you open up your analysis tab, you'll see perhaps your calibration curve and your chromatogram and the processing method and the results. Well, you can also save it as for this calibration table as calibration RS. So I saved it for you in my eWorkflow on the AppsLab digital library. So I made a table for it, a setting. So you don't even need to do that if you don't want to, but it's very easy to do. Oh yes, so I have to brag. So eventually I get to this relative standard error, but there's a story before that. Okay, so been a chemist a long time, kind of proud of being a chemist, the basics things I should be able to do, right? Uh, well, I actually failed 2 or 3 times on the calibration. So what we're doing is essentially pipetting in 200 microliters of the ppm standards, the microgram per mil standards, to create a calibration curve of nanogram of fluoride versus the response. And with the RSC calculations, I mean, even looking at the plots, you have to admit it's not that good. But the RSC calculations are pretty horrid. I think they were 27% or 28%. And keeping in mind, I was supposed to make 20%, right? So here's the calculations. And essentially they're columns. There's the xi is the theoretical, and then the measured value is the column next to it, and then all that, and it's summarized into the RSEs. I had some as high as 45%, so pretty horrid on, oh boy. So there's the summary of it. There are always lessons learned, and in addition to the lessons learned about why it failed, what I learned is actually that precision and accuracy is well demonstrated in this method. So you have precision which is RSD, and you have accuracy, which is RSE, the inverse of it, right? So it's quite a good demonstration. They don't necessarily follow the same trends, nor does the coefficient of determination really follow the same trends. And this exercise definitely brought me on the side saying RC is a better parameter. Okay, so problem solving. So the first thing you always do is you think about, oh, what did I do wrong? Was I daydreaming about the weekend or what I was going to be doing after work? And I messed up on preparing the standards. So of course I redid those, right? And I prepared them from the same intermediate standard. So I figured, oh, not a big deal. I started thinking, well, the EPA suggests that you use a syringe for transferring the PFOS standards. Maybe my pipette tips are contaminating or carrying over contamination. So I switched to the syringe. Then I made maybe new standards from the stock standard. Okay, well, still no good. And I tried it again. And I thought, hey, maybe an automated sampler would be better than me pipetting in. Yeah, but yeah, I do know how to use a pipette. I'm pretty good at it. But what automation often takes care of those human errors. And I tried making the standards again, but to no avail. So now I'm starting to stress out. I'm starting to dream about this stuff at night, questioning my abilities as a chemist and going, oh gosh, should I be thinking about retiring? This is terrible. So worked it through with managing lab and found out that it was the quartz wool. So my good intentions, I was putting a little bit of quartz wool here and there and maybe a little bit more on that boat um, to prevent a possibility of the standard from evaporating, thereby, skewing my results. In fact, I was contributing random variable high contamination to my standards. So after that, okay, now I got a good calibration. Yeah. And you can visually see that it is a much better calibration. But now I'm getting greedy. So this is a quadratic with an offset 1 over weighting on a squared. So more focus on the low end of the samples. But like I said, now I'm greedy. 2% is not good enough. Here we go with linear with offset 1 over a squared weighting. So yes, woohoo! I'm excited. So yeah, confidence, life is good. And so I prepared a fresh batch of working standards and pipe into the known clean ceramic boats and I go home, instead of staying there watching babying over each calibration point. So yeah, forget hanging out. I'm going home. Just load up my samples. Forget those syringe and the liquid sampler. Load up the samples and go home. And yes. So I use this calibration curve then for all my samples. So before we get there, we have to talk about equivalent fluorine. This is in the EPA 1621. You do need to calculate it a little bit just to make sure, but essentially it's the ratio of the formula weight of fluoride versus the compound, the PFOS reagent, times the number of fluorine per molecule times the concentration of the standard itself. And there's my example. So I have a 50 ppm of PFOS standard, PFHX S, and there's the ratio of the two formula weights. There's 13 fluorines in that compound on the 50 milligrams per liter, micrograms per mil, same. And that's my equivalent then fluoride for that standard. And of course, you need that to be able to determine how much to pipette in or syringe in for your spike samples. So task 3, finally get to task 3, now is my 3 days of method blanks and MDLs. So they use the term of MDL-B for blank and MDL-S for standard. These are the two chromatograms of blank and the standard. Calculating the MDL, the blank, and the MDL, the standard. This comes from our old handy dandy Federal Register method, 40 CFR 136 from the Appendix B. And it's essentially here. This is the formula. You don't necessarily need to go to the 40 CFR 136, but if you want, that's what you'll find it. So the MDL for the blank is the mean plus the student t-test value for n equals 7, 99 percentile, 3.14 times the standard deviation of your samples. And the MDLS is probably more familiar. It's the 3.14 times the standard deviation. There's my example. The example looks more complicated than the actual calculation, but you can see here, here's the results. So there's, again, there are 7 samples of each method blank and MDL done over 3 days, and recorded values. So average, standard deviation, RSD, and MDLs. So for this method, using 100 microliter injection and 100 milliliter sample, this is what you can expect for sensitivity. 1.2 for your blanks and 2.5 for your true MDL. Task 4, is part of the initial demonstration of capability. It's determining the initial precision and recovery standard. So we again prepare 25 nanogram per mil equivalent fluoride in that water sample, and we adsorb it onto carbon and analyze then the carbon by combustion IC. And we only need to do 4. So what we're interested in, of course, is the accuracy, which is the recovery, and the precision, which is the RSD. So very straightforward. This value, though, is now used for the OPRs that you'll be doing, the ongoing precision recovery standards you'll do through the process. Okay, so finally we get to samples. There were 9 samples that we were given, many bottles of each. First, we have to determine the initial values. There's shown in the second column there. And then we added 2 levels of PFOS as PFHXS and determined the samples and determined then the recovery. So you can see the recoveries are pretty good in the high 80s to low 100% recovery, as well as the check standards. The CVs are 99 to 109% and the OPR 98 to 101%. I do have to say the blanks have already been subtracted, and samples 2, 3, and 6 had high TSS, so they also require a ceramic wool blank and a ceramic wool inserted between the flow and the 2 granulated activated carbon samples, of which all 3 samples were combusted, right? So the top carbon column, the bottom carbon column, and the ceramic wool was combusted and combined as a sample. Okay, so here's an example of sample 3. It is one of the high TSS samples. Chromatogram A is the original concentration, the sample as received. B and C are where we added 30 ppb of equivalent fluoride to the sample. They're replicates. So I got 90% recovery. So okay, so after all those recovery of different samples, now we're going to focus just on one sample. So we do replicates of all this one sample, and we're going to look at then the recovery of these other materials, these other PFAS compounds. So there's been a lot reported in the literature about these smaller PFAS compounds being more difficult to analyze. The extraction efficiency and the adsorption efficiency are reported to be less than the larger compound, of which we were comparing to PFHS, so the hexane sulfonic acid. But we didn't find that. We found that these compounds, the PFBA and PFOS, and the mixture of lots of different PFAS compounds acted similarly as far as recovery. So this is encouraging because these are the compounds of most concern for our health. So again, the results look about 80% to 110, 114%. So I figured you'd probably want to know what's in that mix. So I'm not going to read them all out to you. This is a standard we all received from Wellington Laboratories. And there's the part number. The fluoride equivalence is 18.2 nanograms per mil. So you look, there's quite a few compounds there, a few acids, a few sulfate compounds, and a bunch of amides, different type of compounds. And here's my chromatography. Looks excellent. Sample 7 was the one selected for this comparison of these different compounds, and it's a very small. The sample 7 contained very little PFOS in general, but it was spiked in with those 2 or 3 different compounds. It looks just fine. So we got to the end here. So on summary. The method itself, EPA 1621, is not yet official, but it's in comment, review, and promulgation, and everyone is expecting it. That'll be official this fall. I wrote up an application document with my results of this collaboration study. It's AN002748, and in it, I demonstrated the power of combustion IC and eliminating the sample matrix and measuring only the AOF content in samples, and successfully achieved those goals for EPA Method 1621. I'd say the EPA has done a great job. It's a rigorous and methodical method, sensitive, down to 2.5 ppb. Okay, so remember our samples were wastewater. Perhaps didn't mention, but our samples for this collaboration study were wastewater. Good accuracy, recovery is 80 to 120%, meeting the requirements for accuracy. Along with ease of use for RFIC, it provides more accurate results as the fluoride is well separated from the water dip, and it makes it easy to integrate the peak. So anytime you have to manually do integration, you're potentially introducing an error, a bias. So also, Cremila can do the RSEs for you, and that should save a lot of time. I do want to point out we have some resources for you. Again, a plug for our Apps Lab digital library. We love it. We put all our applications in there. We attach a Chromeleon e-workflow, which basically is a Chromeleon program. You can download and run the method. And you may have to make adjustments for your instrument or a little bit for the method, but essentially everything you need is in there. And that's where I put that RSE calculation template. But, if you're like me, you probably still do have interest in other instrumentation. So we have lots of GC stuff, LC, ICP-MS, not just IC, but there's many entries there for us. There's our Charlie. So also documents. This is Miss Van Abercrom, Eleonora, the lady that I used her graph, that very interesting graph on AOF versus EOF. She works at the Hessian State Laboratory in Germany. So she worked with our department and generated a customer application note. And we're always open for these. So if you have a great idea on want to get some of your data out, we're glad to work with you in creating a customer application note. And also there's the website Solutions for PFOS Testing as well. Here's the documents supporting EPA 1621. So my colleague, Jingli Wu, developed an application early on for AOX. So this is at ppm levels. It's application note AN72333. But it has similar things. You're looking at adsorbable material analysis by combustion IC, except it's at ppm levels. So cross-contamination is an issue. And here's my document here, AN002748, which is live and available. And I also wrote a tips and tricks for successful implementation. It is in the final processes of review and should be available within a couple weeks. So it's Tech Note 003056. And here are the EPA documents. So there's a single laboratory document on the left, the multi-laboratory document on the right, and in the center, the Method 1621, which again, we expect to be official this fall. So here we go. Right about an hour. You have any questions?
Excellent. Yes, there were many questions in the chat. Let me
Okay.
summarize them and articulate to you. If I miss something, then Brian will help me. So the first question I would generalize. Could you please describe this method assumptions? So what does this method imply? For example, fluoride as measured by combustion IC in here assumes that all fluorine detected comes from PFAS, PFOS.
Yes.
Okay.
So officially, some of the polymers, fluorinated polymers, are not under the classification of PFOS. But that's probably the biggest assumption. The second one is assuming we're getting rid of all the inorganic fluoride. We all have fluoride in our water, and that's why we go through those whole steps about salting, essentially salting the water by adding sodium nitrate in. And it seems very efficient because I know our level, Sunnyvale is like the most analyzed drinking water in the world, right? So that's where we are. So I know what our fluoride level is. And it's compared to PFOS, it's significantly higher than what we would measure for PFOS. And we're not seeing any of that coming through at all. So I'm very positive that that process is eliminating the inorganic fluoride, as well as getting rid of high amounts of chloride, which also could interfere. So I'm very confident about that. That method is set up well with that. What I don't know is what I don't know. So again, the classification of PFOS is a little strange, right? There's some like TFA, that was the one I was looking for. TFA, tetrafluorinated acid, trifluorinate, anyway, TFA. That is not classified according to the EPA as a PFOS material because it can degrade by itself. Now, I probably, again, would not pick that up on the adsorption process because it would be washed away. It's not going to adhere to the carbon. So the only sort of gray area is, one, I can't tell what kind of PFOS compound this is because I'm screening. Two, we probably do pick up some of those bigger compounds. I mean, that's what all of us have been kind of hypothesizing about why those numbers for extractable and AOF are so different. But everybody's been kind of seeing that. So we believe, anyway, we believe it has to do with the larger polymers, but they do contribute to PFAS contamination anyway. So we're getting it. We just need to keep an eye on what those compounds might be.
Yep. And you already answered like the other side of the same question. That is, if I generalize those questions in the chat, how you ensure the completeness of adsorption on the granulated activated carbon of all the PFAS. And then are there any PFOS, PFAS compounds which are not adsorbed by that granulated activated carbon? But you already covered that if you want to
Yeah,
make any
yeah,
comments.
yeah. So we did test pretty small compounds in that collaboration study. Um, the the literature is suggesting that the C3s, C4s might not adsorb. And depending on where the location of the perfluorination is, it might not even fall into classification by EPA as a PFOS compound. But the literature is indicating the C3s and C4s are the toughest. Now I think the smallest we tested was a C4. Yeah, so we did test perfluorinated butane sulfonic acid. That was the smallest we tested, and it seemed to do just fine. And it was kind of a surprising discovery.
Okay.
And so the other one about
Mhm.
adsorbing is the initial method had us compare the top carbon results separately from the bottom carbon results. They were worried about breakthrough. So
Mhm.
that's why there's two carbon columns there. So most of the time there's very little found in the second carbon. But as we, as we go to my idea, as we go to higher volumes to get to those PPT volume numbers, and perhaps the other side, as we go to the higher concentrations, we need to keep an eye on that breakthrough.
Yep. Another question was, what are the other peaks, that is, other than fluoride, on your chromatograms?
Oh, sorry. Yeah. So we all like to know what's there, right? So essentially that gradient is designed to flush everything off the column. So, the whole purpose is we only need to quantitate one peak, but we don't want any other any other analytes there to carry over and disrupt our quantitation on the next run. So I know at least there's chloride and sulfate there and definitely carbonate. But after the first couple of samples, I didn't look for what type of ions they might be. But absolutely, sulfate and chloride are there because that's what's in wastewater, right? Nitrate probably also, though I definitely added nitrate to my sample. And then I added more for rinsing. So I would assume I'm also carrying over some nitrate as well.
Mhm.
And this
Have
is
you seen
wastewater.
phosphorus to get into phosphate ever on combustion IC?
Um, so, uh, so ask the question again.
Yeah, so have you seen phosphorus to go into the phosphate detected after the combustion?
No. So I had to test that for myself. So I was skeptical my first use of combustion IC. So I did test phosphorus compounds, mostly the inorganic, because I just couldn't believe it. Um, and it does not carry over into the ionic phosphate after combustion. I did more investigation and found out that the phosphor compounds need a much higher temperature that normally these combustion systems run at. Um, Pretty much all of us are keeping around 950 to maybe 1100 at the top, centigrade. The phosphorus compounds need 1500 C to pyrolyze. So we're definitely not seeing them at all. And that was good enough for me for understanding the mechanism of why I wasn't seeing it, as well as experimentally not seeing it. So, as IC chemists, we're concerned about it because it can be one of the latest eluting peaks, and so we want to make sure that it's not interfering. But the good side is you can use this for as a internal standard in your absorption fluid if you really want to do something like that. But so it's not going to pass through the combustion oven, but if you introduce it after the combustion oven, you could use it as internal standard if you wanted. We never found a good enough purpose for it.
Yep. Thank you, Terry. Another question was about the throughput concerning like how many samples max you can do per an 8-hour shift. We answered partially, but it's probably good for you to comment as well. So what's the bottleneck and how many samples can you push through?
So typically the adsorption stage is done offline, separate from the instrument, but there's a catch, right? So if your process is out of control, so you need to analyze your method blank and your uh, calibration verification, but that one only goes through the combustion system. But your method blank and your OPR goes through adsorption, adsorption. So you need to combust those to make sure your process is in control before you run all those samples. So if you're confident your process is under control, you're definitely going to be running the adsorption separately from the combustion IC. I was running, see, my runtime is longer, right, with that, using that standard EPA method. So I was running maybe about 2 sequences a day. So that's 10, 20 samples a day. But because I was only doing it by myself, I would come in and adsorb all the samples in the morning and then run the samples overnight by combustion IC. So the two things are required, right? The process has to be in control, and you could have someone else doing the adsorption. So this prepping the samples for the combustion system. But be aware with bracketing, if those checks fail, then all those samples should be rejected. Their analysis, you have to repeat them. So.
Okay. I will also generalize and combine two additional questions. So if you do not have to follow the exact EPA method protocol, or if you apply the combustion IC to some other systems, then can you speed up this screening process? And when you answer this question, could you please mention if you've observed any difference when using carbonate eluent versus hydroxide eluent? Maybe you can also touch on how we can speed up things if you have to with one element versus another.
So the carbonate eluents, generally it's okay. So the carbonate eluents is our old style chemistry. We're all comfortable with it and it's easy to use, but it has two downsides. One is, in general, the sensitivity is lower because your baseline of the IC is higher. Okay, so you have to do things to it to remove that carbonate out of the baseline so that you could see more trees for the forest, right? So if the total baseline is high, all you see is a little peak, and this can impact your sensitivity. So hydroxide has a definite advantage over that. For sample loading, again, we essentially can load the same amount of sample, but the sensitivity is somewhat lost by using the carbonate. For running a faster run, the only requirement is that that retention time. It has to be more than 1 minute. Fluoride has to elute more than 1 minute longer than the water dip. And of
But
course it
that's for
has,
EPA method only
yes,
in discussion. Yep.
yes. So, yes. So, but if you're not following the EPA method, you definitely want to have at least half a minute or more. You want to be in the flat part of the chromatogram after it goes through the water dip and is in a flat zone, because carbonate has a big, broad, wide dip, and it kind of comes out of that dip in a kind of sloped manner. And that is not a great place to quantitate. So fluoride typically is going to be your first peak out. It's generally not retained well. That's the advantage of the AS24, is it holds it much longer. We are allowed to play around with the so if we have to follow EPA 1621, we are allowed to play around with the gradient as long as we meet that criteria. If you're not interested in EPA 1621, you still should make sure that your chromatography is good enough, better than so-so, right? So you want it to be out of the dip, past the slope area in a flat section, and that is going to be close to half to 1 minute out of the water dip. Now with carbonate, again, that's another disadvantage, is that it's a huge water dip. So you actually lose some time because it takes time for all that water to come through, right? So ours is with hydroxide. I mean, we have carbonate chemistry too. We just prefer to use hydroxide for element generation.
Yep, because of all the advantages it gives you. Yep.
Yeah.
Another question, actually two that I can see in the chat. Can you use emulsions as your analyte sample metrics and still detect with IC the fluoride? So can you combust emulsion samples?
So excluding AOF, which I would assume would cause kind of a gooey mess, I have done emulsions directly through combustion IC. That it's been in the news lately. BVO, the brominated vegetable oil that's in some of our soda pops, yeah, the yellow orange ones. Yeah, I did an application on that, and it is definitely an emulsion. I mean, that's its whole purpose in life, is to keep the citrate in suspension in the drink, and I use combustion IC for that. It's another way to get around matrix issues. I would not feel comfortable injecting that into the IC. And of course, the BVO is in the flocculent portion of that sample, because I did filter and found out that no, there's none in there.
Same person's second question kind of is, any concerns using polymers as your form of analytes that you combust?
No, no. So we also have some of those on the books. I think most of our polymers that we did were either printed circuit boards or polyethylene. Those are not the dirtiest samples you have to worry about, really. They're more the petroleum goo and sludge and things that they have to deal with. The polymers, actually, it's a great method to look at the corrosive ions in polymers. So.
Okay. I think last question, and then Brian, if I missed some, please turn on your microphone and articulate it for Terri so she doesn't need to read through. So the last one I think is, did you have to do a dilution factor to ensure good chromatography for certain analytes? Because you said that this method requires fluoride to be below 8 ppm. So what would happen to your chromatography if sample is above? So that's first part of the question. And second is, your calibration curve is made with a 200 microliter injection, and the samples are actually in the absorber are with 100 microliter.
100 mil, yes.
100 mil, yeah.
Yeah. So, okay, so keep me on track for both of those. Okay, so dilution. So the dilution is for the adsorption stage. So directly to the IC, if we were able to, if the analytes were actually high enough concentration, that's not an issue. That the IC and combustion IC can handle that pretty well. It's the adsorption stage. You want to make sure you are not causing the carbon, your analytes, to break through. You want to trap them. And the concern with the higher fluoride and the higher chloride is, in fact, it could take up active sites in the carbon, thereby preventing adsorption of your PFOS. So that's the reason why that's done. And that's why it's in the method. Remember, EPA always puts in interferences and potential interferences and what they suggest you do about them. And the second question was, the difference in volumes. So I calibrated by nanograms, so weight of mass, nanograms of fluoride. So my units then are going to be mils. So my concentration actually on calibration is nanograms per mil. So it's around, so for example, half a milligram per liter is 100 nanograms on column. Okay. For the samples, those are 100 mils. So I take my nanograms given out by my calibration curve and then divide it by 100 mils. And that's why we're using the adsorption. It's a concentration mode. It's a way to get that 100 mils of sample into my IC. We're adsorbing and combusting, just getting the analytes left into our IC.
Have you ever done any soil samples by combustion IC for PFAS or for anything else?
I've done some minerals. I was going to say we had a PFAS soil, an NIST standard for soil. I'm not sure if we did it directly. I know at that time we were looking at extraction, but I'm not sure. The amount of sample that we can use into the boat would be about 100 milligrams for a fluffy sample, fluffy sample that's low density and and relatively moderate concentrations. So 100 milligrams is kind of like our bottom point. If it's a high concentration, then we can add in maybe only 25 or 15. So we're kind of trying to balance the amount of concentration in the samples.
Yeah, so I would highlight that getting sample as soil as a sample would be a different introduction of that sample into the combustion furnace. So you just use a auto sampler with a boat.
Yes. Yeah.
Yep. Okay.
I mean,
Go
theoretically,
ahead.
we could like swirl it in water and then do the absorption stage, but we know PFAS sticks to particles. So we would then have to combust the sample anyway, right? Yeah.
Okay. So let me try to unmute everyone and see if anyone is interested in asking the question verbally. If you can switch on your camera, that would be great. But if you cannot, just go ahead and ask your question. Just a second. Let me see if I can do that.
Oh, I didn't mention we have a couple other PFOS methods coming out. My colleague, again, Jing Li, is working on some textiles and food packaging on those. So we've been doing quite a bit on PFAS lately. Everybody's talking about PFAS, and
Yep,
so are we. Um, but yeah, another topic for another day.
yep. So I believe that now you guys can actually unmute yourself and turn on the camera if you wish, and go ahead and ask your question, especially if I missed articulating your question to Terri from the chat. Please go ahead.
So I have a question, I guess, a clarification on this the soil procedure.
Yes.
If you're combusting the soil directly, would you not be determining total fluoride and not necessarily organic fluoride?
Yes.
Okay, yeah, I think just want to make sure that that distinction is there.
Yeah, you could essentially rinse the soil just to make sure, and then analyze the rinsate for by adsorption and CIC,
Mhm.
just to make sure. Yeah.
Well, it's good, something for us to consider. Thank you.
Yeah,
Thank you,
thank you
Ralph.
for catching that.
We have 2 minutes left in the proclaimed duration of our lovely conversation. So anyone who is willing, unmute yourself and articulate your question.
Have you tried
There.
lowering? I'm sorry.
Oh,
Have you?
sorry. Thank you for the presentation. My question was, are you anticipating that we could quantify fluoride content at part per trillion, part per billion levels?
We can definitely do it part per billion. Part per trillion is keeping me up at night. I'm been thinking about all the different ways we can get there. Of course, loading the column more, right? What if I pre-concentrate, from the IC side? Can I also adsorb more onto the carbon? That carbon has a size limitation of, a weight, size, volume limitation for it to go into the combustion IC. So I think the biggest limitation will be how much volume can that carbon tolerate. So for example, so we all know, right? We're getting ppb, we need to get to ppt, so that's 1,000 times. So I already have 100 mils of sample going onto these little carbons. What if I try to put 10 liters onto those carbon? It might take a long time, but is it actually going to adsorb onto that carbon? Or because it's such a large volume flushing through, would it all, collect somewhere else? So I've been running those calculations through my head, like I said, thinking about it overnight quite a bit. And I think I can approach 10 part per trillion, but the last step is really dependent on that carbon. So I know I can pre-concentrate by loading more sample onto a concentrator column after I combust it, right? And I can load a lot more volume of sample after I combust it onto the IC. So that should give me at least 100 times there. But I don't know if the reason they only let us do 100 mil sample is the limitations of the GAC, the granulated activated carbon. I think it is. I think there is some limitation there. If we go to a different matrix for adsorption, Then we get into the EOF area, and that's going to defeat the whole purpose. Let's say we go for a WAX material. Now we have to get it back off. And yeah, so I think we can get at least, like I said, 10 PPT, I'm thinking. The cleanliness things that we have to go through are going to be very hair-pulling, to say.
Paramount to everything else, I would say,
Yeah,
right?
yeah. Because like I mentioned before, we definitely found that we have to go to the most expensive and the cleanest methanol to not introduce further PFOS into our samples, just from methanol. Who knew? Who knew that was going to be a problem? So there's lots of different areas yet we'll still have to clean up. And the baseline level of the carbon itself is close. Well, it's the method blank right now for 100 mils. Okay, because there's hardly,
I'm going to also say the
you
most
know,
obvious here is that the PPT is the requirement when you analyze for individual PFAS compounds. And here, because it's a screening method, I don't really think we need to go into PPT because we determine the total, not individual PFAS. Okay. Anybody else? Any other questions? Please go ahead and unmute and articulate. Brian, did we miss any questions in the chat? Did I miss any questions in the chat for Terri to answer?
No, I don't think so. I think we covered them. My latest answer was more of CIC in general, not necessarily for PFAS. I was just trying to share the different kinds of samples that combustion IC can do.
yeah, we have a whole bunch there. Again, in our apps lab.
Yep.
Yeah, I know that labs up here in Washington are looking at cardboard, packaging material and cardboard.
So I can recommend right off the bat, organic grinding, because you have got a really non-homogenized sample. I mean, a heterogeneous sample. You want to get it as homogenized as possible. And it's also very fluffy. So another trick is, again, those samples are probably going to be pretty high because we've been analyzing them ourselves. And to keep them in the cup or in the boat, you can add a little bit of water. DI water, okay, fresh from the tap, not sitting in a squirt bottle. But yeah,
Just to cling the particles together.
yeah.
Okay.
So they don't blow away before you get them combusted.
Okay. Very good. Well, it's impressive. 35 minutes of uninterrupted flow of questions.
Yeah, that's cool.
It's a pretty
I
good
like it when
outline.
people ask questions. Yeah.
Okay, well, very good, and thank you everyone for attendance. And very big Russian-style ground vote to you, Terri, for presenting all this.
Oh, sure. It was
So,
a good year of my life here. So yeah.
okay, could you please give us a dismissal from this event, and I will shut it down then.
Okay. All right. Thank you, everybody, and have a great day.
Okay,
Great job as usual, Terri.
everyone,
Talk to you
thank
soon.
you. Cheers.